Okay, so welcome to Advanced Functions 12. Uh, so uh, these series of videos will be recorded by myself. So hopefully you'll learn something from advanced functions, and hopefully it'll help you. So this first lesson that we will talk about is about the power functions. So hopefully by the end of this lesson, you'll be able to express polynomial um, expressions or recognize them and the equation of polynomial functions and be able to use examples from linear and quadratic as examples of polynomial functions. And we also want to be able to determine the degree and the leading coefficient of the polynomial function and be able to describe the features of a power function, such as the domain, range, intercepts, and behavior and symmetry. And last thing is that we want to be able to describe intervals using both inequalities and interval notation, but we'll save that for the ending. Okay, so first of all, the power function is basically the simplest form of the polynomial function, and it simply has the form f of x is equal to ax to the n, where a is the coefficient, where x is the variable, and n is the exponent. Now keep in mind that n has to be a whole number. And then x can be any real number. So we use the symbol x is an element of the real numbers, and a is a coefficient, which is also a real number. Okay, so with these three as a base, so because it's the simplest form, a polynomial expression is basically a series of power functions it represented in decreasing order. So if we have an x to the n plus an minus 1 x to the power n minus 1 and plus dot 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 plus a 2 x squared plus a1x plus a0. Now here we note that the n coefficients from a0, a1, all the way until an are coefficients. The coefficients. We also say that x is the variable. And n is the exponent. And using the same assumptions above, where n is a whole number, x is a real number, and a0 to all the way to an are real numbers as well. Okay, so there are three things that we can say about the polynomial expression, is that for n, we could say that the degree of the polynomial which is going to be the largest exponent of the greatest power of x. So for example, according to the definition, the degree of the polynomial expression in this form is going to be n. So because it's representing the largest exponent. Now an here is going to be called the leading coefficient. And this will let us determine the direction of the polynomial. For example, if we have a negative leading coefficient, then it would go in the opposite. It's going to be reflected in the x-axis, or if it's positive, then it's going to be in the normal form. So a little visual. This is when the leading coefficient is positive, which is like your simple quadratic function. And this is what happens when you have a negative leading coefficient. We see that, so an is greater than 0. This one, an is less than 0. Okay, so for a0, last one, is simply just a constant term, which tells you whether to move up the function or down the function. So moves up or down. All right, so with these in mind, we can use the definition that we have formed for polynomial expressions to form the definition of the polynomial function. So a polynomial function simply has the form f of x is equal to an x to the n plus an minus 1 x to the power n minus 1 plus dot 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 plus a1x plus a0. So that's the polynomial function. But just for this lesson here, we are going to be focusing on power functions, mainly focusing on definition 1 here. Okay, so let's move on. So for example, let's say we're given the following functions and we want to determine whether they're polynomial functions or not. But if there are polynomial functions, then we'll state their degree and leading coefficients. But if not, let's explain why. Okay, so for the first one, part A, we have f of x is equal to 4x cubed minus 3x squared plus x. All right, so obviously, according to the definition that we have up here, definition 3, part A is a polynomial function. So from this, we know that it's a polynomial function. So let's say, let's have a look at the degree. So the degree here is a largest exponent of the greatest power of x. So in our case, 3, we always look at the first term, which will let us know what the highest degree is. So in this case, 3 is our degree. And the leading coefficient here is the coefficient of the highest degree, which is going to be 4. I forgot to put here. Is the coefficient an is supposed to be the coefficient of the highest exponent. But sometimes you may say, well, what if the polynomial function was rearranged so that their degrees are not in the right order? For example, let's say we have something like y is equal to x plus x cubed minus x squared. What if we have something like this? Well, the degree here, we simply have to look at what is the highest degree between each of these x, x cubed, and x squared. Well, remember that x has a power of 1. So between these 3 numbers or variables, we see that x cubed has the highest degree. So that means x cubed has to be the highest degree. not x1, not x2. And the leading coefficient has to be based on the highest degree, as mentioned. So obviously we could just rewrite this a little. Y is equal to x cubed minus x squared plus x. All right, so continuing on. So part B, we have g of x is given by negative 9x to the fifth plus 3/4 x squared plus 15. Well, obviously this is also a polynomial function because it's expressed in the form axn x to the power n plus an minus 1 x to the power n minus 1 and so on. So we could say that part B is also a polynomial function. So that means we have to state the degree and the leading coefficient. So the degree here is the highest, largest exponent of x, which is going to be 5. And the leading coefficient is negative 9. All right, so the last two examples, part C and part D, both of them are not going to be polynomial functions because for C, we actually have a trigonometric function. You have a trigonometric function, which is not a polynomial function. And part D is also not a polynomial function because it's an exponent, exponential function. Okay, so based on previous years, we have worked with linear functions of the form f of x is equal to ax plus b, and quadratic functions of the form f of x is equal to ax squared plus bx plus c. So both of these examples are examples of power functions. If we say that b was to equal to 0, and here we would have b and c equal to 0. So those would be power functions. And polynomial functions as well if b and c were not equal to 0. But let's say that we want to explore higher order power functions and be able to describe their similarities between them. Okay, so for even degree functions, let's start with this one. So an even degree function is a polynomial function whose highest degree power in a polynomial is even. So from this, there are two possible cases. For the first case, we could have a positive leading coefficient and an even degree. So for example, let's take x squared, for example, or 2x squared. So let's say that we have the function on the left side, we have y is equal to 2x squared. So for this one, we know that it's simply just going to be like a parabola. So it's going to be pointing upwards. And we say that, okay, based on the quadrants that it's going to go to, so the quadrants are simply the parts of the Cartesian plane that is divided into 4. And usually it's numbered by 1, 2, 3, 4 as going in a counterclockwise direction. So like this. So based on this, the leading coefficient is positive and we have an even degree. So we see that, okay, as we go down from quadrant 2 and then goes up to quadrant 1. So that means every positive leading coefficient and even degree would go from quadrant 2 all the way to quadrant 1. So it would go from quadrant 2 to quadrant 1. Now the second case here, what if we have a negative leading coefficient? So if we have a negative leading coefficient, but still an even degree, so for example, let's have a look at a sketch. Now let's say we have negative 2x squared instead. Then it will look something like this. So we see that based on the quadrant, it will go from negative quadrant 3 all the way to quadrant 4 if you read the graph from left to right. So we would say that it would go from quadrant 3 to quadrant 1 or 4. Okay, so from these two cases, we introduce the idea of end behavior, which determines the direction of x as x gets larger or x gets large negative. So we describe the end behavior as follows. So for the first case, we would say that as x approaches infinity, so meaning that as x gets larger, we would say that f of x, the function, would also get larger. Because if we see from the graph this way, if it gets larger, it's also going to get larger as well. And same thing for the other direction. As x approaches negative infinity, f of x also approaches infinity. Because if we see here, as x gets larger negative, it's also going to be approaching infinity. For the other case though, so this is for case 1, and then this one's for case 2 down here. So we see that as x approaches infinity, so as x gets larger this way, we see that it's going to go to negative infinity then. So f of x is going to go to negative infinity, and similarly as x approaches negative infinity, f of x also goes to negative infinity. Okay, so from these two cases, we have concluded that a positive leading coefficient and an even degree will go from quadrant 2 to quadrant 1. And similarly, for a negative leading coefficient and even degree, it will go from quadrant 3 to quadrant 4. All right, so we had a look at the even degrees, but what about the odd degrees? So an odd degree is an odd degree function, which is a polynomial function whose highest degree power in the polynomial is odd. So from this, there's also two possible cases. So first case, let's say we have a positive leading coefficient. And an odd degree. So for example, let's use the space below. So let's say we have a positive leading coefficient and something like this. So that would be like saying y is equal to x cubed, for example. So a here, the coefficient is going to be 1. So we have a positive leading coefficient and an odd degree. We see that it's going to start from quadrant 3 in this area here, and then it's going to go all the way to quadrant 1. which is true for all positive leading coefficients and odd degree. So that means we would say that it goes from quadrant 3 to quadrant 1. Now, similarly, instead of a positive, let's say we have a negative leading coefficient. So for a negative leading coefficient, and an odd degree. So let's say we have negative x cubed. So y here, negative x cubed, for example. Then we would say that we see that, okay, it's going to start in quadrant 2 and end up in quadrant 4 as we read the graph from left to right. So we would say that it would start in quadrant 2 and it ends up in quadrant 4. Now, similarly, how we did the end behaviors that we described in for the even degree functions, let's do the same for the odd degree functions. So we see here that, okay, for the first case, we see that, okay, as x gets larger, positive, it's going to go to infinity. So like as x approaches infinity, f of x also approaches infinity. But as we see that, okay, as x gets larger negative, so negative infinity, it's going to go to negative infinity as well. So as x approaches negative infinity, f of x approaches negative infinity. Now, same thing for negative x cubed. So this is for the second case. We see that as x approaches negative infinity, so let's start with that. So negative infinity, it's going to go to positive infinity. So we see the direction of the arrow is going to point to positive infinity. So we see that f of x approaches infinity. So, and similarly, as x approaches infinity, f of x will approach negative infinity. Okay, so those are the two cases. So to recap a little, we see that if we have a positive leading coefficient and an even degree, it's going to go from quadrant 2 to quadrant 1. And if we have a negative leading coefficient but an even degree, then it's going to go from quadrant 3 to quadrant 4. And for this one, for odd degree functions, we say that if we have a positive leading coefficient and an odd degree, then it's going to go from quadrant 3 to quadrant 1. And last one, if we have a negative leading coefficient and an odd degree, then it's going to go from quadrant 2 to quadrant 4. All right. So moving on. So let's talk about symmetry a little. There are two types of symmetry. For the first one, there's line symmetry, which basically divides the shape into two congruent parts. So it divides the shape into two congruent parts. So let's do a quick sketch. So for example, let's say we have a parabola. Then we would see that, okay, if we draw the line down the y-axis here, we're going to get two congruent parts. So we would have one on this side, and we would also have the other on this side as well. Okay, so usually for line symmetry, if you want line symmetry to occur for even degree functions, so it can only occur for even degree functions, all polynomials must be even to have line symmetry at x is equal to 0. So it's always going to occur at the line x is equal to 0 here if we want it to have a line symmetry. And it can only occur between even degree polynomials. So for example, we would have x to the 6th plus x to the 4th plus x squared, and so on. So for the other case, the second one, we would consider point symmetry, which is a special case for odd degree functions. So point symmetry simply rotates a point 180 degrees from point, so in the opposite direction. So for example, let's say we take a odd degree function. So let's say, so we take this function. All right, so we're going to take a point. So let's say the center, the origin 0, 0, and we rotate it 180 degrees. So every point here is going to be rotated 180 degrees around the center point. So we would see that each of the points that are on this side are all going to be rotated 180 degrees this way. Now this would only occur with odd degree functions. So all polynomials must be odd. All right. So for example, we can say, so for 0, 0, that's the point of inflection. It's an inflection point, or you could call it point symmetry as well. And it only occurs when you have odd degree polynomials. So like x to the 5th plus x cubed plus x, and so on. All right, so we looked at the symmetry and we looked at odd and even functions. Let's have a look at another example. So let's say that we want to state the degree leading coefficient. So degree is the first, second is the leading coefficient, whether it's even or odd, and the end behavior. So let's start with part A. So for 2 of x, the degree here is going to be 1, and the leading coefficient is 2. So degree is 1, and leading coefficient 2. Well, because the degree is odd, it's going to be an odd function. So I'm just going to put odd. Then for the end behaviors, so because we have a positive leading coefficient and it's odd, then we know that it's going to go from quadrant 3 to quadrant 1. So we could just say quadrant 3 to quadrant 1. Or we could do it another way, where we could say it as x approaches infinity, f of x approaches infinity, and as x approaches negative infinity, f of x will also approach negative infinity. Okay. So second one, we have a degree of 6 and a leading coefficient of 5. So because 6 is an even number, the function is going to be even. So with positive leading coefficient and even degree, the function is going to go from quadrant 2 to quadrant 1. Now for the third one, we have a degree 2 and leading coefficient of -3. Well, because we have an even exponent, the function is going to be even. Now, because we have a negative leading coefficient, it's going to go from quadrant 3 to quadrant 4. For the seventh, x to the 7th, we have a degree of 7 and a leading coefficient of 1. So if there's no number next to a variable, assume that it's going to be 1. So because we have an odd exponent, the function is going to be odd. Now let's do the end behaviors in how we represent it in this way over here. So, oh, nope, okay. So that means if we have, so we would say that as x approaches infinity, f of x approaches infinity. As x approaches negative infinity, f of x also approaches negative infinity. And similarly for the other four, so part E, we have a leading coefficient of -2/5 and a degree 9. So we have a degree that is odd, so the function is going to be odd. So for the end behavior, we have as x approaches infinity, f of x will approach negative infinity. And as x approaches negative infinity, f of x will approach infinity. And I could leave the other three, so part F, part G, and part H. You guys could try these on your own, so I'll leave that as homework, just for exercises. Okay, so let's have a look at another example. So it's given the sketches of the functions. So there's actually 3 functions. So let's determine the domain, the range, the end behavior, and any symmetry. Okay, so I'm going to divide each of them into 3 parts. Okay, let's have a look at part A. So part A, we want to determine the domain and range. So the domain, if you recall, is the set of all x values. Set of all x values. And the range is the set of all y values. Okay, so the domain, how we would state this, is simply as follows. So we would usually have D to represent the domain is equal to the set x And we always start with x is any real number. So x is in real numbers means that x could be any number. So from the graph, you'd see that, okay, x can go to infinity, no problems. And we could see that it could also go to negative infinity without any problems. Same thing for the range. So now for the range is the set for all y values. And here we see that the y's will have no problems, and the y's would also have no problems in the other direction. So we would say that y is also any real number, can be any real numbers. And for the second part, we state the end behaviors. So as x approaches infinity, we would see that, okay, as it goes to infinity, it's going to go to negative infinity. So f of x goes to negative infinity. And as x approaches in negative infinity, we see that it's going to go to positive infinity. So f of x approaches infinity. Now, if we want to determine any symmetry now, we would see that, okay, it's an odd degree function. X is an odd degree function. So that means if we rotate every point 180 degrees, we should get the same sort of value, but on the opposite side. So it's going to go in the opposite direction. So we would say that it has point symmetry. At 0, 0. All right. So now for part 2, we have a parabola standard, and we want to state the domain and range as well. So for the domain, we would see that, okay, as x gets larger and x gets negative larger, we would see that it has no problems. So we're going to say that x can be any real number with no restrictions. And then for the range, we still have y as any real number. However, we see that the function is always going to be greater than 0. So we know that parabolas will always be greater than 0. And for the domain and range, or end behaviors, so we say that as x approaches infinity, f of x will also approach infinity. And as x approaches negative infinity, f of x approaches positive infinity. And so last thing that we see that we have a line symmetry at x is equal to 0. Okay. So the parabola shape given by half x squared is generally true for any even degree functions. For example, if we take x to the 4th, we would also see that it sort of has a parabola shape as well. All right, so the last example, I could leave this for homework or for you guys to try. So let's move on. So let's talk about the interval notation for last. Okay, so usually we would describe graphs in a variety of ways. Basically, that could describe the set of real numbers. So there are two forms where we could express them. For one, we could use interval notation, and the second one, we could also use inequalities. So for example, as an inequality, we could write them as -3 less than or equal to x less than 5. And equivalently, in interval notation, we would write this as x has to be in -3 and 5, but 5 is not inclusive because it's less than 5. So visually on the number line, we would, so let's draw the number line. So here is, let's say, 0, -1, -2, -3, 1, 2, 3, 4, 5. This is not to scale, but we should get the idea. So here's -3, and here is +5. So -3 is going to be equal. It can be equal because we have this negative sign, this equal sign down here. So that's why we fill in the circle whenever we have a equal sign there. But at the 5, since 5 does not have the equal sign, this has to be drawn like a circle, basically meaning that we don't include the 5. And so we also connect the line or connect the points together. So it looks like that. So that's basically representing the inequality -3 less than or equal to x less than 5, or written like this in interval notation. So intervals that are infinite are expressed either using positive infinity or negative infinity. So square brackets, as we see with the -3, indicate that the end value is included. So meaning that from the example above, you see that -3 is included. And we also use round brackets, like in the 5 here, to indicate that the end value is not included. So, and last one is that we also use round brackets to express infinity. So let's have a look at the example. So example 4, so let's say we want to convert the following to inequalities to interval notation or interval notation to bracket notation. So for the first one, we would see that, okay, that we would convert it to interval notation. The end values are not included because we have less than and less than, and it does not have the equal sign below it. So converting it to interval notation, we simply have x in 1, 2, which simply means that x is between 1 and 2. If we look at it as a number line point of view, so it would be something like this. That's between x is between 1 and 2. All right, so for the second one, part B, we convert it to inequalities now. This should be inequalities. And so we see that the 5 is included this time, but not the -3. So we would write this as -3 less than, but not equal to, x less than or equal to 5s, because the 5 is included as well. Then for the third example, part C, we see that, okay, we have -10, but which is inclusive. So we would say that x in -10, so we use the square, and 2, but is not inclusive. So we use round. And similar for part D, we have both that are round square brackets. So we would write them as -5 less than or equal to x less than or equal to 1. So both are included. So we have both the equal signs. Now for the last 5 examples, we would see that, okay, we only have one region that we consider. So for x is greater than or equal to 4, if we have a look at this on a numbered line, for example, and let's say that, okay, over here is 4. We would see that, okay, so x greater or equal to 4 So we start here, it's inclusive, and it's just going to be anything larger. So it's going to go to infinity. So we would write this in bracket notation or interval notation as x is an element of 4 inclusive to infinity, but round brackets using infinity. And in part F, similarly, we have 7 to infinity, but this time the 7 is not included. So we would say that x is just greater than 7, and it can go until infinity. Now, similarly for x is less than or equal to 3, on a number line, so we would have a look at this from backwards. So say we start -3 here, and it goes to negative infinity. So here's -3. So we would write this as x is in negative infinity to -3, inclusive. And similarly, for x from negative infinity to 2, we would write this as x less than 2. Now, for the last one, part I, is a little bit interesting. So whenever we see this r, that means it's a set of real numbers. So there are two ways that we could express this. For one, if we were to use interval notation, we would write this as x is in negative infinity, comma, infinity. So that's one way we could write this. Or if we were to use inequalities, we would have negative infinity less than x less than infinity. Okay, so all of that said, we have finished with section 1.1, which we talked about the power functions. So to recap, in the beginning, we talked about the definition of the polynomial function, what the parts of the polynomial function represent, and we also had a look at even, odd functions and also the symmetry as well. And we also had a look at a couple of examples, how to describe these power functions. And last thing, we had a look at interval notation, which we just had a look at how to express them using both ways, both using inequalities and interval notation. All right, so that's going to wrap things up for today. So if you have any questions, just let me know down in the comments.